This is part 2 of the Chapter 2 lectures, and we're starting with slide 22. We're going to talk about chemical reactions. Chemical reactions occur when atoms or when compounds and molecules, when chemical bonds break between compounds and molecules and atoms and ions. Basically, in a chemical reaction, you're going to have a chemical change. So the reactant and the product are going to be different. They're going to be different substances. That's the important thing. So in a chemical reaction, the reactants are basically like the ingredients in a recipe. They're the substances that enter the reaction, and then products are the substances that are formed. They are the result of the reaction. So they form after the reaction takes place. In anatomy and physiology, we really talk mostly just about synthesis reactions and breakdown reactions. So a synthesis reaction is often a reaction called a dehydration. And I was thinking of the wrong word. I'm sorry. A dehydration synthesis reaction is the most common type of synthesis reaction. But all of the synthesis reactions, the reactions that build larger molecules, all of those in our body are called anabolism. All those synthesis reactions. But most of the time, the reactions that are important to us in anatomy and physiology are going to be dehydration synthesis reactions. Dehydration synthesis reactions end up taking two smaller molecules, forming a larger molecule, and then removing water. So water forms as one of the products, and that's why it's called dehydration. So glucose and fructose, for example, are simple sugars, and sucrose is a combination of glucose plus fructose. So it's a what we call a disaccharide, which is a sugar that has two simple sugars. So this would be an example when glucose combines with fructose to form sucrose or table sugar, and water is also formed as a product. That is an example of a dehydration reaction, dehydration synthesis reaction. And just a plain synthesis reaction is shown down here at the bottom beside the word example. ADP stands for adenosine diphosphate. So it has two phosphates. So when a phosphate is added to it, it now becomes ATP or adenosine triphosphate. And so it is a larger molecule, so that's a synthesis reaction. But a decomposition reaction is a breakdown reaction. And decomposition reactions, all of the decomposition reactions in our body are called catabolism. So metabolism is all the chemical reactions together. That's all of the anabolic reactions and all the catabolic reactions. All of the building reactions and breakdown reactions are called metabolism. So we can see that there's an example here of a decomposition reaction called hydrolysis. And hydrolysis is a decomposition reaction that uses water. So it's the opposite of the reaction we just saw on the previous slide, the dehydration synthesis. When you have a molecule like sucrose and you add water to it, it breaks apart into simpler sugars, glucose and fructose. And that is a hydrolysis reaction. Just a plain decomposition reaction is shown at the top when ATP breaks down into ADP plus phosphate. That is a decomposition or breakdown reaction. So the main thing is metabolism refers to all the chemical reactions in our body. Catabolism is all of the decomposition or breakdown reactions. And a lot of times those decomposition reactions are called hydrolysis reactions because one of the reactants is water. And the other group of chemical reactions in our metabolism are called anabolism. And they are synthesis reactions. And a lot of times they will be dehydration synthesis reactions because water is formed as a product. Okay, so that's an overview. And we'll talk a little bit about energy, but basically potential energy or stored energy is found in the stored within the chemical bonds of a compound or molecule. And then kinetic energy is energy in motion. So sometimes stored energy is used to create kinetic energy. I'm just going to skip some of this. A chemical reaction can be, there's ways to speed it up and make it occur at a faster rate or a slower rate. A catalyst is a substance that speeds up a chemical reaction. And in the human body, most of our catalysts are enzymes, which are proteins, special proteins that speed up chemical reactions. But also, you can increase the concentration of the reactants, and that will speed up the reaction rate. And you can raise the temperature to a certain extent, that will speed up the reaction rate. Now, at a certain point, it will also, when it's too hot, it will denature the chemicals. But when you raise the temperature and it's still, a level that the chemicals can tolerate, raising the temperature often will increase the rate that the chemical reaction occurs. A catalyst, again, increases the rate of a reaction, and a special type of catalyst is an enzyme. It's a protein catalyst that increases the rate of reactions within the human body. And the way enzymes do this is they lower the activation energy for specific chemical reactions. So for a particular reaction, for example, here's the energy of the reactants, and then this is the energy required for those reactants to react. So there's an activation energy that's required for the reactants to react and become products. If you add an enzyme, if you have enzymes that come in and bond to the reactants, it will lower that activation energy. It will lower the energy needed for the reaction to take place, and that will cause the reaction to take place in a faster time. And again, like I said before, the higher the concentration of the reactants, the faster the rate, and the higher the temperature, the faster the rate. Now we're going to talk about acids and bases. Acids are chemicals that can donate hydrogen ions, and we also call hydrogen ions protons, because a hydrogen ion is literally just a proton. I don't know if you remember when we talked about the hydrogen atom, but the hydrogen atom contains one proton and one electron. So when it loses the electron and becomes a hydrogen ion with a +1 charge, then all it really is a proton. So proton and hydrogen ion with a plus charge are used interchangeably. So any chemical that donates a proton or a hydrogen ion, H+, to a solution is an acid. Acids have a pH below 7. 7 would be a neutral pH. An example of a strong acid is HCl or hydrochloric acid. A base is not going to donate a proton or hydrogen ion, but it's going to accept a hydrogen ion or a proton. The pH of a base is going to be above 7, and one example of a strong base is sodium hydroxide. And sodium hydroxide will remove or accept hydrogen ions from solution. Acids will add hydrogen ions to the solution. All right, so when we talk about acids and bases, we need to a little bit review the pH scale. The scale refers to the concentration of H+ in solution, or the concentration of hydrogen ions or protons, whichever word that you want to use. H+ ion concentration is gives us the pH measurement. Okay, so if the pH is less than 7, it's going to have more H plus than OH minus. If the pH is 7, it will have equal amounts of H plus and OH minus. And if it's above 7, that should be an O there. Sorry, that should have an O. If it's above 7, then it's going to be basic, or alkaline is another word for basic, and it will have more OH minus than H plus. Now, OH minus is hydroxide. H plus, we just say hydrogen ion. OH minus, we just say hydroxide. I will go ahead and change that because that's confusing. So right here needs to be, oh, it's not going to let me. Yeah, it's like it was copied as an image, but that should be OH. So maybe if I just go, I can just go like, let's try this. No, it's not. I'm not going to be able to do anything without it being trouble. So let me find our slide. Here we go. All right. Sorry about that. But this should be an OH, and I don't know how to change it. So the hydrogen ion is going to be high if the pH is low, and the OH minus, or hydroxide ion concentration, will be high when the pH is high. Okay, and it says here pH and hydrogen ion concentration are inversely related. That means the higher the H plus concentration, the lower the pH. Blood pH is between 7.35 and 7.45, which is slightly basic. But anytime blood pH goes above 7.45, that is too basic. So we call it alkalosis. Person is in alkalosis. That can happen if you get dehydrated, severely dehydrated, if you have vomiting. And if your blood pH is below 7.35, that is called acidosis. Both conditions are very dangerous. And acidosis can happen, for example, if you're diabetic and your blood sugar is high. This is an example of some common substances and their pH levels. You can see stomach acid has a very high pH. A very low pH. But a very high concentration of hydrogen. Whereas coffee is acidic, urine is acidic, but not as acidic as stomach acid. Blood is slightly basic. Distilled water is neutral. And then you have some other basic substances, starting with baking soda, is mostly types of cleaners, or bases. Okay, and a salt just consists of a positive ion other than hydrogen and a negative ion other than hydroxide. So if it contains H plus or OH minus, then it's not going to be called a salt. It'll be called an acid or a base. But if it contains a positive ion and a negative ion, like sodium chloride contains sodium, which is positive, and chloride, which is negative, then we call that a salt. And there are other salts. Sodium chloride is the most common one, and it is the chemical formula for table salt, but there are other salts. Salts would be anything where you have a positive ion joined with a negative ion, as long as neither ion is hydrogen or hydroxide. So as long as it's not H or OH, as long as neither one of these is an H or an OH, then we call it a salt. When it's a positive ion joined with a negative ion, we call it a salt. Okay, we also have chemicals that we call buffers, and buffers will resist pH changes. So when you have a buffer and an acid is added to the buffered solution, the buffer will bind to the excess hydrogen ion, and that will remove it from solution and prevent the pH from going down. So that's what a buffer does. When you add an acid to a solution that has buffer in it, the buffer will cause the pH to stay the same, even though without the buffer, the pH is going to drop. But with a buffer, the buffer itself will bind to the excess hydrogen ion that's released by the acid, and it will prevent the pH from going down, prevent a decrease in pH. Okay, and we're also going to talk about organic chemistry versus inorganic chemistry. Organic chemistry tends to be, is always substances that contain carbon, but there are some exceptions. Carbon dioxide is not organic. It's an inorganic molecule. For the organic chemicals, they're going to have carbon, but they're also going to contain hydrogen. So organic is going to have carbon and hydrogen together. That's the easiest way. That's the easiest way to remember organic chemicals. They're going to have carbon and hydrogen both. Whereas if you just have carbon with no hydrogen, like you do with carbon dioxide, that's going to be an inorganic chemical. Now, we're on slide 43. We're going to stop here, and I'll start the next recording at slide 44.